Find the number of distinct positive integer valued solutions to the equation a plus b plus c equals 9. So what we are looking for is integers a, b, and c, which are all positive and are all integers which solve this equation. Well, let's list a couple of examples here. A is equal to 1, b is equal to 1, c is equal to 7. That one right there solves that equation because 1 plus 1 plus 7 is equal to 9. Here's another solution. A is equal to 1, b is equal to 7, c is equal to 1. Here's a third. A is equal to 7, b is equal to 1, c is equal to 1. Now at this point I have expended all of the 7-1-1 combinations, so now I can go to a different set. This time let's try a equals 1, b equals 2, c is equal to 6. So I've got one of the 1, 2, 6 ways of doing things. Then I've got to go, 1, 6, 2, 6, 1, 2. So I've got a bunch of different ways to list these out. You can see there's a lot of different combinations that you'd have to run through. And this is with a right-hand side of 9. You could imagine if instead of having a 9 over here on the right, you had something like a 100, this would be absolutely impossible. So I'm going to try to solve this problem instead using a combinatorics approach. And I'm going to do that by drawing 9 dots here. So there are 9 dots, and I can put bars anywhere I want in 2 positions between these dots. So for example, if I put one of the bars, let's say right here, and the other bar, let's say I put it right here, then what we have is we have 4 dots that fall here, 3 dots falling between the bars, and then 2 to the right of the bars. And that right there corresponds to the solution 4 plus 3 plus 2 equals 9, which of course is the same as one of these solutions here that we had down the line. Eventually we would have run into it. A equals 4, b equals 3, c is equal to 2. But I've kind of framed it now in a different fashion with 9 dots, and I put 2 bars, and the bars are indistinguishable. You can't tell one from the other. If we swap the 2 bars, for example, we'd still have 4 plus 3 plus 2. And those bars have to be put between the dots here, and that's what gives you positive integer valued solutions. Once you frame it this way, it becomes a combinatorics problem, and the solution is as follows. There are 8 gaps between the 9 dots, and I want to pick 2 of those gaps. So 8, choose 2. And the reason I use combinations rather than the permutations here is these bars are indistinguishable. If I switch the order of the bars, it wouldn't matter. So the order with which you pick these 2 positions is not relevant. So it is 8, choose 2 different ways of solving that equation, and that's going to be 8 factorial divided by 2 factorial, 6 factorial. Notice that up top you have 8 times 7 times 6 times 5 times 4 times 3 times 2. But all you need is an 8 times 7 because 6 and down on the 8 factorial cancel with the 6 factorial down here. So all you have is 8 times 7 divided by 2 times 1. 8 times 7 is 56. 2 times 1 is 2. 56 divided by 2 is 28. So if I would have completed this list, I would have had 28 different distinct positive integer valued solutions to this particular equation.